Hi there. In this video, I want to apply conservation of energy to problem solving for the first time. So we're going to talk about conservation of energy with problem solving, or with problems. All right, with problem solving. Okay. So conservation of energy, you've heard it said in words, as energy cannot be created or destroyed. And that's true. But we are going to use conservation of energy as the equation E initial equals E final for a closed system. I call this conservation of energy in the narrow sense. What I mean by, well, first let me say what I mean by a closed system. A closed system pretty much means, I think, what you would guess, which is that no energy is allowed to transfer out of the system, no energy is allowed to transfer into the system. So a good example of a closed system is dropping a ball in a vacuum, just kinetic energy transferring into gravitational potential energy. There's nobody coming in from the outside hitting the ball, giving it extra kinetic energy. There's nobody coming in from the outside stopping the ball and reducing its kinetic energy. So that's a closed system, ball in a vacuum dropping in free fall. If you don't have a closed system, the opposite of a closed system is an open system, then you have to say that the initial energy equals the final energy plus or minus some energy transfers. So energy can't be created or destroyed, but if I want to get rid of some of this marker's energy, I can transfer it to something else, right? If I throw this marker and it's got some kinetic energy because it's coming in and it's in the air, and then I catch it, I've reduced its kinetic energy and I've transferred that kinetic energy out of the marker in a variety of places. But we're not going to do, for starters, we're going to do problem solving in scenarios where we don't have to worry about energy transfers into or out of the system. So this is our equation, arguably the most important equation, we'll study this whole year. Energy initial equals energy final. It is the narrow sense of conservation of energy that does not allow for transfers. Okay, so let's do a problem and let's use this equation in a problem. So example 1. You throw a ball 2 meters off the ground. And you throw a ball at an angle of 30 degrees above the horizontal. Leaving your hand one meter above the ground. At an initial speed of 15 meters per second. It's about 30 miles an hour. It's a good chuck, but it's possible for most of us. So how fast is it going? When it is 4 meters off the ground. Okay. So, the first thing you might think about is kinematics. And you can do this problem with kinematics. However, you don't have to, and it's much easier not to. With kinematics, you have to break this velocity, this 15 meters per second, you have to break it up into vertical and horizontal components. Then you have to do the horizontal, kinematics. Speed's not changing in the horizontal direction. You have to do the vertical kinematics. Plug in your y initial as 1 meter. Where did I write that? 1 meter. Plug in your y initial as 1 meter. Plug in your y final as 4 meters. Okay, it's doable. You know how to do it, but let's not. Instead, let's draw an initial and a final diagram. and let's draw an energy bar chart. So an initial diagram, we've got me, or you, I suppose. The ball's here, it's going this way, velocity is 15 meters per second. We've got an angle there as well. That's initial. Final, you're still here, the ball's probably gone quite a bit. Now it is 4 meters off the ground, so it's higher. I don't really know if it's going up or going down. I'll just pick arbitrarily. And we want to know how fast it's going, V question mark. So this is our initial diagram, and this is our final diagram. So now I'm going to write down my energy bar charts. Initially, I have kinetic and potential. Until I do some math, I might not know right away which one's bigger, and that's okay. But I'm going to write them both down. This is initial. And then final, I also have potential and kinetic. Now right away I might not know about kinetic, whether it's going faster or slower, but I do know that it's higher off the ground, right? It's 4 meters off the ground instead of 1 meter off the ground. So I'm going to draw UG as bigger than it was. It doesn't necessarily have to be as big as anything else. It's just comparing it to what it was. It needs to be bigger. And if we're ignoring air resistance, which we will here, then the sum of these two boxes should be about the same height as the sum of these two boxes, so that means that kinetic has to go down some. I don't know how high, but it should at least look plausible that these two boxes added together are the same as those. Okay, so keep in mind, of course, you can always come back in the video if you want to reread the question, but now I'm going to erase it, so hopefully I can remember all of the given information. I think I've written, no, I haven't written the heights down, but the initial height is 1 meter and the final height is 4. So, now I'm going to write down E initial equals E final. Again, because we're going to ignore air resistance in this problem, we can assume that there are no energy transfers. So E initial equals E final. Okay. So that's what I'm going to work on. I'm going to work on the two sides of it separately. So E initial equals, well, I have some kinetic energy, 1/2 mv initial squared, plus mgh initial. Okay. I'm going to keep filling in information that I know. So E initial equals, this is 1/2 m, which isn't given, 15 squared, plus m times 9.8 times 1. Okay. And so I have E initial equals, that's 225 over 2, so it's m times 225 over 2. That's a 5. It's 5. There we go. Sort of looks like 5. Plus 9.8. And I have an m in here. Okay, maybe Mr. Saunders forgot to give you enough information. We'll see. And so I've worked on the E initial side. So at some point, I'm probably going to take this here and plug it in on the left-hand side of this equation, but I haven't gotten there yet. Now I'm going to work on the E final side. E final, again, it's going to be the same thing, 1/2 mv final squared plus mgh final. So E final equals 1/2 m, or V final is what we're looking for, we don't know that. M times 9.8 times 4. Okay. And so we get E final equals, it's not too much simplification I can make here. I guess I'll factor out, I'll just leave it as is. I'm going to multiply that 9.8 and the 4 together. 1/2 mv final squared plus m times, oh right, that's 39.2 m. So now I'm going to do some algebra. The color that looks different. So I'm going to take this and I'm going to plug it in here. And I'm going to take this and I'm going to plug it in here. Okay. And in order to do that, I think I'll get rid of my top diagrams. So now I'm working on E initial equals E final. I guess I'll write that one more time. E initial equals E final. E initial is m times 225 over 225 over 2 is 112.5 plus 9.8, which I'm going to want to add here in a minute, equals, and again we have 1/2 mv final squared plus 39.2 m. So, whew, Mr. Saunders did give us enough information, although it felt like we were going to need to know the mass. It turned out that the mass cancels, and this will always happen if you only have gravitational and kinetic energy. If those are the only two types of energy changing hands, then the mass will show up in every term here, and it'll cancel out of every term. So that's nice. It's a nice little FYI. So if you ever feel like you need to know the mass, but you don't know the mass, pretend you know it, leave it as an M and hope it cancels. So here we have, let's see, here we have 122.3 equals 1/2 v final squared plus 39.2, right? Yeah, I need to keep erasing. Yeah. And then subtract 39 from both sides and multiply by 2, take the square root. So v final squared equals 122.3 minus 39.2, all times 2, times 2. So v final equals So V final equals 12.9 meters per second. And we did that without needing to take any components. And we found the overall velocity, not the x velocity or the y velocity, because kinetic energy doesn't care about x or y velocity. It cares about the velocity, the whole value of the velocity. This v is not a component, so that's the whole thing. So if all you care about is the overall velocity in a problem, and all you're given is overall velocity, it usually makes sense to try conservation of energy before kinematics. It's simpler. This problem-solving process was much simpler than it would have been to solve that problem with kinematics, which you can verify by doing it with kinematics. So you've seen that we start with E initial equals E final. We work on the initial side, write down as much information as we know, as we can figure out about E initial. Work on the E final side, write down as much information as we can about E final, set them equal to each other, and solve for the variable that we're looking for. So that's your very first conservation of energy problem.